When physicists talk about a particle, they are operating a strange linguistic double standard. On one hand, the term describes a physical object, something tangible. On the other, it refers to a mathematical abstraction that can burst into existence and vanish back into a vacuum. For centuries, our physical intuition demanded that for a particle to exist, it needed a well-defined location. And if that object moves, it follows a continuous trajectory through spacetime, traveling from point A to point B without any gaps. This bubble chamber tracks moving objects, confirming physical intuition. Unbroken lines trace continuous paths of particles. But at the center right, intuition fails. A new spiral track originates from nothing. The object was created at this vertex and will eventually be annihilated. Classical kinematics assumes that objects last forever. It cannot describe a physical reality where things lack a permanent existence. This failure is why physicist Steven Weinberg advocated for a rigorous, alternative definition. Instead of relying on physical analogies, he defined a particle as an irreducible representation of the Poincare group. Modern quantum physics requires a foundation that can account for this instability. If a particle isn't a permanent object, we need a definition based on the rules of the environment it exists in. That foundation begins with the mathematician Henri Poincare. He gave his name to the Poincare group, the collection of spacetime symmetries that leave the laws of physics unchanged. Those symmetries operate on a specific stage defined by Hermann Minkowski. His mathematical grid combined 3 dimensions of space with one of time. On this grid, we find our first symmetry, translation. If you run a physics experiment and then shift that experiment 10 meters to the left, or wait 10 minutes to run it again, the results are identical. The second symmetry is spatial rotation. If you take that same system and turn it to face any direction in 3-dimensional space, the laws of physics are preserved. The final symmetry is the Lorentz boost, pulled from special relativity. This dictates that observing the system from a different constant velocity also preserves those laws. When you combine all possible translations, rotations, and boosts into a single mathematical structure, you have the complete Poincare group. If we move past the requirement of a physical trajectory, our new baseline is this. A fundamental particle is something that mathematically obeys all of these universal spacetime rules. The physicist Eugene Wigner took on the challenge of translating these geometric spacetime transformations into the framework of quantum mechanics. He used representation theory. This is a mathematical process that converts spatial actions, like physically rotating an object, into numerical matrices that calculate quantum states. Wigner analyzed these complex mathematical operations to find what was irreducible. He would break the operations apart until he reached the smallest, indivisible core mathematical objects. Wigner proved that these smallest, irreducible matrix blocks map to what we identify as particles. When you categorize these irreducible blocks, 2 unchangeable mathematical labels emerge from the equations. The first invariant label derived from the symmetry equations corresponds to what physicists measure as mass. The second invariant label derived from those equations corresponds to the quantum property of spin. This is the rigorous definition found in quantum field theory. A particle is a specific mathematical state defined by mass and spin, transforming according to these spacetime symmetries. Properties like mass and spin are the mathematical consequences of existing within a Minkowski spacetime. They are the invariants of the system. This abstract definition introduces an immediate question. If a particle is a mathematical representation of symmetry, is it actually real? In quantum field theory, physical reality is dependent on the energy scale at which you probe an interaction. At lower energies, or macroscopic scales, the math allows us to treat the interaction as if it involved discrete, point-like objects. In this domain, the classical description of a particle is accurate and useful for calculating outcomes. But as we shift our focus to high-energy, subnuclear regimes, the descriptions change. As the probe scale shrinks, the concept of a point-like object dissolves into overlapping, wave-like interference ripples spreading across a continuous field. Neither the discrete particle nor the continuous wave is a universally true description on its own. Physicists apply the specific effective description that matches the energy scale being measured. The debate between particle and field is a false dichotomy. They are 2 facets of the same underlying quantum reality, revealed at different resolutions. This brings us back to the linguistic tension physicists navigate. using the same word to describe pure math and a physical object. Look once more at the physical consequence, the visible event that triggers a detector in a lab. Compare those tracks to the abstract Wigner and Weinberg representation theory. They seem disconnected. Yet the tangible track left in a detector is the localized consequence of that abstract symmetry matrix operating at a specific scale. To a practicing physicist, both are real. The mathematical framework is real, and the physical object interacting with its environment is real. Quantum field theory accounts for both perspectives. The physical definition and the mathematical one describe different aspects of the same phenomenon. The term particle serves as a single label for two things: the abstract symmetry of the theory and the localized event we measure in the lab.